September 19, 1944. A dense, rolling fog hung over the fields near Arracourt, France, turning the countryside into a ghostly landscape of shadow and mist. First Lieutenant Merwin then gripped the rim of his Sherman tank's turret, his knuckles widening. His gunner's eye stayed glued to the periscope, scanning the mist for any sign of German armor. The 37th Tank Battalion had been warned, Panthers were lurking. These German tanks, with their sloped armor and lethal 75mm high-velocity guns, had a reputation for being nearly impervious to the standard American rounds. Most Shermans could barely scratch their frontal armor. But Men and his crew carried a secret, tucked into the Sherman's ammunition rack, 6 M93 high-velocity armor-piercing rounds. Each was built around a tungsten carbide core, a tiny technological marvel capable of turning an ordinary Sherman into a tank killer that German crews would soon fear. These 6 rounds wouldn't just punch holes in steel, they would shatter assumptions, forcing German tankers to reconsider everything they believed about American armored forces. The psychological impact of this ammunition would rival its physical destructive power. The story of these rounds began far from the battlefields of France, in the industrial and testing facilities of the United States. Metallurgists and ballistic engineers raced against time in early 1944, attempting to solve a crisis that threatened American armored divisions. The M4 Sherman, the backbone of U.S. tank forces, was failing against the Panther. The Panther, designed to counter the Soviet T-34, combined a powerful 75mm gun with an 80mm sloped glassy plate. The effective armor thickness, about 140mm, made frontal penetration nearly impossible with standard American shells. Intelligence had underestimated both the numbers and the technical superiority of Panthers. By June 1944, at the Normandy landings, Panthers made up 38% of German armored forces, a massive increase over predictions. The standard 75mm M3 gun on most Shermans could not penetrate a Panther's frontal armor at any range. Even the upgraded 76mm M1 gun, arriving in limited numbers by July 1944, struggled to pierce the Panther's sloped armor except at dangerously close distances, often under 100 meters. Engaging under those conditions was almost suicidal, given the Panther's long-range firepower, capable of destroying a Sherman at over 2,000 meters. It wasn't a failure of the guns themselves, it was a failure of ammunition. The 76mm rounds initially deployed, M62 armor-piercing capped rounds, could punch through 109mm of armor at 1,000 meters. That was enough against Panzer IVs and assault guns, but Panther's frontal armor remained a fortress. The first M4 Shermans mounting 76mm guns rolled off U.S. production lines in January 1944, reaching Britain by April. Yet, despite availability, commanders hesitated to deploy them on D-Day. Crews were undertrained, logistics were complicated by multiple ammo types, and most critically, American leadership underestimated the resistance they would face. By early July 1944, the reality in Normandy was grim. Reports of the 75mm gun's ineffectiveness reached General Dwight Eisenhower. His frustration was palpable. The Wonder Gun had failed against what was supposed to be manageable opposition. A board convened in mid-July confirmed what tank crews had already learned: the Sherman could not reliably defeat a Panther frontally. Commanders scrambled. By July 25, during Operation Cobra, 102 M4A1 76mm Shermans finally saw combat. Reports were sobering. While an improvement, the 76mm still required careful tactics, aiming for flanks or weak spots to have a chance at killing a Panther. The breakthrough came from American ingenuity in metallurgy and physics. Engineers developed the T4 round, later standardized as the M93 HVAP, high-velocity armor-piercing ammunition. These rounds featured tungsten carbide cores enveloped in lightweight aluminum, designed to maximize kinetic energy while minimizing weight. Muzzle velocity jumped from 792 meters per second for standard rounds to over 1,036 meters per second, an increase that directly translated into unprecedented penetration power. At 1,000 yards, these rounds could penetrate 160 millimeters of armor at 10 degrees obliquity. Panther gun mantlets, previously near impenetrable, could now be targeted reliably. The first HVP rounds arrived in Europe in August 1944, but production was slow. Tungsten was scarce, sourced primarily from China and supplemented domestically. Each Sherman carried 6 HVP rounds, consuming nearly 5 kilograms of the strategic material per tank. Supply shortages meant tank crews had to use these rounds judiciously. September 1944 brought the American breakout into Lorraine. Patton's Third Army was pushing hard toward Germany, with logistics stretched to the limit. The 4th Armored Division seized a bridgehead over the Moselle River at Arracourt, threatening the heart of the Reich. The German 5th Panzer Army, under General Otto von Manschufel, launched a counterattack with 2 freshly formed panzer brigades, including 42 Panthers. On paper, the Germans outnumbered the Americans nearly 3:1. Yet, tactical errors, inexperience, and American preparation would turn the tide. Fog shrouded the battlefield on the morning of September 19th. Panther crews, inexperienced and moving in rigid columns without reconnaissance, blundered into prepared American positions. Captain Kenneth R. Lamison Sherman crews, briefed on the HVP rounds, waited. At barely 75 meters, the first Panther emerged. A single HVP round struck the gun mantlet. The turret exploded from secondary detonation, and 2 more Panthers fell in rapid succession. Throughout the morning, similar engagements erupted. American forces, using the fog for concealment, targeted vulnerable spots with precision. M18 Hellcat tank destroyers, faster and equipped with HVP rounds, struck with deadly efficiency. Coordinated artillery and P-47 Thunderbolt fighter support amplified the effect, turning the battlefield into a nightmare for German crews. The Panther's technical superiority was nullified by combined arms doctrine, superior tactics, and the new HVP ammunition. By the end of the engagements, 86 German tanks and assault guns were destroyed, while Americans lost 25 Shermans and 7 tank destroyers. Beyond the tactical victory, the psychological impact on both sides was profound. American crews gained confidence, while German crews realized their once invulnerable tanks could be defeated. Reports reached German high command suggesting secret heavy guns or British support, but the reality, the industrial ingenuity and resource availability of the Americans, was far more troubling. By late 1944, the impact of American HVP ammunition on German armored operations became increasingly evident. Interviews with German tank crews after the war revealed a common theme: the threat posed by improved Sherman rounds fundamentally altered their tactical mindset. No longer could Panther or Tiger crews rely solely on their thick armor for protection. Awareness that American Shermans could penetrate their mantlets at combat range forced German crews to adopt more cautious strategies, slower advances, and heavy reliance on defensive positions. This defensive posture played directly into American hands. U.S. armored doctrine emphasized mobility, combined arms coordination, and aggressive exploitation of enemy hesitation. Panthers and Tigers, formidable individually, were less effective when forced into static defensive roles. The psychological toll of losing their previously unmatched confidence caused German crews to hesitate in critical moments, allowing American units to seize initiative and dictate the pace of engagement. Technical analyses of HVP projectiles recovered from battlefields further illuminated the innovative design of these rounds. The tungsten carbide core, encased in lightweight aluminum, represented a masterful use of scarce materials. This combination allowed the core to retain immense kinetic energy over distance, while the aluminum carrier minimized barrel wear and facilitated higher muzzle velocities. German engineers recognized these advantages but were hampered by dwindling resources and relentless Allied bombing campaigns. Germany simply lacked the industrial capacity to produce comparable rounds in sufficient quantities, leaving their tanks reliant on ammunition designs from 1942 and 1943. The strategic implications were profound. While the Panther's 75mm KWK-42L/70 gun was formidable, capable of neutralizing most Allied armor, its effectiveness relied heavily on the assumption that opposing crews would remain cautious. HVP rounds undermined that assumption, proving that technological superiority alone could not guarantee battlefield success without adequate logistical and operational support. The Battle of Arracourt exemplified this lesson. American forces, supported by superior logistics, coordinated artillery, and air power, could overcome technically superior German tanks. The psychological impact of HVP ammunition on American tank crews was equally important. Units that had faced Panthers in Normandy, often under harrowing conditions, were initially wary and defensive. The arrival of HVP gave them confidence. Suddenly, the seemingly invincible Panther was a target that could be defeated under the right circumstances. This confidence translated into more aggressive tactics, faster decision-making, and effective exploitation of terrain. For German crews, the erosion of the sense of invulnerability, the core of their morale, resulted in hesitancy, slower maneuvers, and increased caution, which cumulatively degraded combat effectiveness. Highly decorated Panther ace Otto Carius later reflected in his memoirs how facing Shermans armed with HVP profoundly affected crews' psychology. The psychological dimension of armored warfare, confidence, fear, and the perception of invulnerability, proved as decisive as technical specifications. Panther crews, previously aggressive, became cautious and conservative in combat, a shift that had measurable tactical consequences. Beyond individual engagements, HVP demonstrated the critical importance of industrial capacity in modern warfare. Both German and American engineers understood the physics of armor penetration. Both recognized the potential of tungsten-cored rounds. But while the Americans had the industrial resources to produce HVP in significant quantities, Germany could barely manufacture enough for limited testing. This discrepancy repeated across multiple weapon systems. Germany developed technically superior weapons, from jet aircraft to advanced tanks, but could not field them in numbers sufficient to affect strategic outcomes. Conversely, American industry produced vast quantities of effective, if technically less sophisticated, equipment, which in overwhelming numbers could dominate the battlefield. The M4 Sherman exemplified this approach. Technically, it was inferior to the Panther in armor and gun power. Yet, approximately 49,324 Shermans were produced compared to only 6,132 Panthers, an 8-to-1 production ratio. When combined with the arrival of HVP ammunition, this overwhelming numerical advantage proved strategically decisive. The legacy of these engagements extended beyond World War II. Lieutenant Colonel Creighton Abrams, commander of the 37th Tank Battalion at Arracourt, rose to become U.S. Army Chief of Staff. The lessons he learned, combined arms coordination, crew training, ammunition effectiveness, and logistical planning, directly influenced the design of the M1 Abrams main battle tank. The Abrams incorporated a powerful 120mm smoothbore gun and advanced ammunition, including depleted uranium penetrators, embodying the same principles HVP introduced in World War II. Similarly, German veterans who joined the Bundeswehr after the war applied their lessons in designing post-war armored doctrine. They understood that superior technology alone could not overcome numerical disadvantages or supply limitations. This philosophy informed the Leopard 1 and Leopard 2 programs, emphasizing high-quality training, effective ammunition, and tactics tailored to the constraints of national industrial capacity. Post-war examinations of battlefield wrecks confirmed VAP's effectiveness. Analysis revealed that Shermans equipped with HVP could reliably penetrate Panther mantlets and turret faces at favorable angles, though the glassy plate remained largely resistant. These findings validated tactical doctrines emphasizing flanking maneuvers and engagement at optimal angles. While HVP did not eliminate German tanks, it shifted the balance of psychological and tactical power. The broader lesson extended into modern armored warfare. Effective ammunition, concentrated kinetic energy, and crew proficiency remain decisive factors. Modern tank rounds, including tungsten and depleted uranium penetrators, build upon the foundation laid by HVP. Soviet and Russian ammunition development followed parallel paths, recognizing that armor-piercing capability depended on projectile density, velocity, and energy transfer rather than merely armor thickness. September 19, 1944, therefore marks not just a tactical milestone but a turning point in the psychology of armored warfare. American crews, once hesitant and cautious, gained confidence to confront German heavy tanks directly. German crews, previously confident behind thick armor, were forced into defensive, cautious behavior, constrained by the knowledge that they could be defeated frontally. HVP, produced in limited quantities but applied intelligently, transformed the battlefield dynamic, illustrating the intersection of industrial capacity, material science, tactical doctrine, and human psychology. The experience at Arracourt shaped armored warfare doctrine for decades. It demonstrated that superior production, logistical support, tactical training, and targeted technological improvements could overcome technical disadvantages. The cumulative lessons of VAP's introduction, the transformation of Sherman crews, and the adaptation of German tankers continue to influence military planners and engineers today, reminding us that in war, victory often depends on more than just the quality of a weapon, it depends on how it is used, supported, and psychologically leveraged. The first rounds fired by Lieutenant Men and his crew, watching tungsten cores pierce seemingly invulnerable Panther mantlets, underscored the profound lesson that thoughtful application of resources, combined with tactical acumen and morale, could reshape the course of battle. This lesson remains as relevant today as it did in the misty fields of Arracourt, where American ingenuity met German technical prowess, and history was written in steel and fire. The skies over Europe in 1944 were a theater of technological innovation, industrial might, and relentless human courage. Among the thousands of engagements shaping the course of World War II, the introduction of high-velocity armor-piercing, HVP, ammunition represented a turning point in armored warfare. This is the story of how American ingenuity, logistical superiority, and tactical doctrine transformed hesitant Sherman crews into confident adversaries capable of challenging the formidable Panthers and Tigers of Nazi Germany. By the summer of 1944, American tank crews in Normandy faced a grim reality. The German Panther, with its long-barreled 75mm gun and sloped frontal armor, could destroy Shermans at ranges where the Allies' standard ammunition struggled to penetrate. The psychological impact was profound. Crews landed in France knowing that they faced a machine designed to instill fear. Casualty reports from June and July painted a stark picture. Untested crews often froze under the shadow of German steel, and operational momentum slowed as units adapted to these deadly threats. But the American response was both technical and tactical. Engineers in the United States developed HVP ammunition, a specialized round that combined a tungsten carbide core with a lightweight aluminum carrier. The result was a projectile that could retain extreme kinetic energy over distance, while allowing higher velocities without excessive wear on the Sherman's barrel. In the laboratory, these rounds represented a remarkable fusion of physics, material science, and industrial efficiency. In the field, they became a psychological weapon as much as a technical one. The first combat use of HVP by Lieutenant Merwin Men's Sherman crew at Arracourt on September 19, 1944, marked a decisive moment. Panthers that had once seemed invulnerable now faced a projectile capable of piercing their mantlets. German tankers, trained to rely on armor for confidence and aggression, found themselves vulnerable. This shift reshaped tactical thinking on both sides. German engineers quickly studied captured HVP rounds. They recognized the design brilliance, a tungsten core that maximized penetration and aluminum casing that preserved barrel life. Yet Germany faced an insurmountable challenge: industrial limitations, scarcity of tungsten, and constant Allied bombing prevented them from producing sufficient HVP equivalents. By late 1944, German tank production focused not on innovation, but maintaining the output of existing designs, relying on older rounds from 1942 and 1943. The Battle of Arracourt demonstrated the fundamental truth of modern warfare: technology alone does not win battles. American tanks, less technically advanced individually, leveraged combined arms coordination, superior logistics, and overwhelming numerical superiority. A Panther might defeat a single Sherman under the right circumstances, but when faced with coordinated units, flanking maneuvers, and air and artillery support, even the most advanced German armor became vulnerable. VAP's psychological impact cannot be overstated. American crews, previously cautious and defensive, gained confidence. They began to move aggressively, take calculated risks, and exploit terrain. German crews, conversely, were forced into defensive postures. Highly decorated tank aces like Otto Carius later reflected on how this erosion of invulnerability affected morale and operational effectiveness. The Panther's mantlet, once a symbol of invincibility, became a point of fear. The broader strategic implications extended beyond a single battle. The U.S. could produce thousands of Shermans and HVAP rounds, while Germany struggled to field limited quantities of technically superior tanks and weapons. Production numbers tell the story: approximately 49,324 Shermans versus 6,132 Panthers, a ratio of over 8-1. When combined with improved ammunition, training, and tactical doctrine, this industrial advantage proved decisive. The lessons of Arracourt extended into post-war armored doctrine. Lieutenant Colonel Creighton Abrams, who commanded the 37th Tank Battalion at Arracourt, rose to become U.S. Army Chief of Staff. His experiences shaped the design of the M1 Abrams, a tank incorporating a powerful 120mm smoothbore gun and depleted uranium penetrators, echoing VAP's principle of concentrating extreme kinetic energy in a dense projectile. German veterans of Panther units, later involved in West Germany's Bundeswehr, applied their wartime lessons to Leopard 1 and Leopard 2 designs, emphasizing crew training, effective ammunition, and tactical flexibility in recognition of industrial limitations. The psychological and operational lessons of facing a numerically superior, resource-rich enemy informed Cold War armored doctrine as much as the technical lessons did. Post-war battlefield analyses confirmed VAP's effectiveness. Shermans equipped with these rounds penetrated Panther mantlets and turret faces at favorable angles, while the glassy plate remained largely resistant. These observations validated tactical doctrines emphasizing maneuver, flanking, and engagement at optimal angles. American doctrine evolved to integrate these lessons into crew training, logistics planning, and combined arms operations, reinforcing the idea that battlefield success depends on a synergy of technology, tactics, and morale. The transformation of American tank crews from hesitant defenders in June 1944 to confident attackers by early 1945 reflected a combination of factors: months of combat experience, improved training, increased availability of 76mm Shermans, and HVAP ammunition. Crews learned to exploit opportunities, engage effectively, and maintain initiative. The confidence gained in small units scaled across divisions, shaping operational outcomes throughout the European theater. Modern tank warfare continues to reflect lessons learned during these critical months. Depleted uranium and tungsten alloy penetrators, combined with advanced fire control systems, embody the same principles HVP introduced. Globally, engineers recognize that armor-piercing effectiveness depends on projectile density, velocity, and kinetic energy concentration rather than sheer armor thickness. The HVAP experience demonstrated the enduring truth: technological innovation must align with industrial capacity, tactical doctrine, and psychological readiness to influence the battlefield meaningfully. September 19, 1944, remains a symbolic turning point. The first HVP rounds fired at Arracourt reshaped armored warfare. American crews gained the confidence to challenge previously invincible opponents. German crews faced the sobering reality that their armor was no longer absolute protection. Industrial ingenuity, tactical coordination, and human courage converged, shaping the outcome of battles, the course of campaigns, and the evolution of modern military technology. The lessons learned from HVAP, Sherman tanks, and Arracourt extend beyond history books. They remain relevant for military planners, engineers, and tacticians facing the challenges of modern combat. They teach that a well-coordinated force, leveraging technological innovation intelligently, can overcome seemingly insurmountable challenges. And they remind us that in the crucible of war, confidence, morale, and the effective application of resources often matter as much as steel and gunpowder. By late 1944, the industrial might of the United States had become one of the decisive factors shaping the outcome of armored engagements in Europe. While German engineers could design technically superior weapons, including the Panther and Tiger tanks, the reality of war was that design excellence alone could not win battles. Factories under constant threat from Allied bombing, shortages of critical raw materials like tungsten, and stretched supply lines limited Germany's ability to translate technical superiority into battlefield dominance. American industry, by contrast, operated at a scale and efficiency that transformed material resources into combat power. Tens of thousands of M4 Sherman tanks rolled off assembly lines, accompanied by specialized ammunition like HVAP. This sheer volume ensured that even if some tanks were lost in combat, replacements were immediately available, preventing the loss of momentum that often plagued German operations. Logistics. The timely delivery of fuel, ammunition, spare parts, and trained personnel amplified this advantage, allowing American forces to sustain offensives over hundreds of kilometers of contested territory. The contrast could not have been starker. German tank units often faced delays due to ammunition shortages, breakdowns, or insufficient fuel. Even the most experienced crews found their operational freedom constrained by the limits of what their supply chains could provide. Meanwhile, American units moved with unprecedented speed and coordination. Frontline commanders could rely on continuous resupply, artillery support, and air cover, making aggressive maneuvers not just possible, but tactically sound. HVAP ammunition perfectly illustrates this principle. Its effectiveness depended not only on superior materials and engineering but also on the ability to deliver it to the right unit at the right time. American logistical systems ensured that HVAP rounds reached Sherman units engaged with Panthers, creating localized advantages that multiplied across the battlefield. German crews, aware of these limitations, were forced into defensive postures, unable to counter the sustained pressure imposed by numerically superior and well-supplied American forces. The lesson was clear: industrial capacity and logistics were as decisive as technological sophistication. A weapon's potential mattered little if it could not be produced in sufficient numbers, distributed effectively, and supported by trained crews. The synergy of production, supply, and operational planning allowed the Allies to translate material superiority into tactical victories and strategic momentum, ultimately shaping the course of the war in Europe. In conclusion, the story of HVAP, Sherman tanks, and the Battle of Arracourt is as much a story of factories, railroads, and supply depots as it is of battlefield heroism. Industrial capacity turned engineering potential into tangible battlefield power, while logistics ensured that technology reached the soldiers who needed it most. Without these foundations, even the most advanced weapons designs would have remained ineffective. This enduring lesson resonates far beyond World War II, reminding military planners that wars are ultimately won not just by superior machines, but by the capacity to produce, deliver, and sustain them in the chaos of battle.